Physics 2211 Lab 2. My name is Yashad Garude. So the purpose of this lab was to drop an object and record the motion of the object and experiment with online code to prove the change with and without drag force on the object, as well as observing Newton's second law of motion. So basically I just dropped like a can in my room. It was very light, and as you can see in the pictures, this is Newton's second law, so force equals change in momentum with change in time. And here's some equation that I used. Obviously F equals ma is very important to Newton's second law. And here's just a random picture I found on the internet of like someone dropping something to show that I dropped an object. Next, so the background, using the net force to find the changing velocity during the drop, and also taking account of gravity and drag force in the experiment to remake my results in the code. So I had to just make sure I included gravity in the code when I was remaking the frames and the position, so that it would be the same as when I did it in the tracker. And here are just some equations as well. Final velocity equals vi initial velocity plus at, and because of f equals ma, which is Newton's second law, a equals f divided by m, and it's substituted here to get the new equation. And this equation right here is from the previous lab, which we reused. And then obviously the kinematics with velocity update formula and position update formula. Alright, and then we'll go to tracker. So this is the video that I recorded, and it's a quick video. Yeah, just me dropping the can. Here's the tracker, obviously you can see that. And then here is the bottom graph is a more important one, with the position of the y and the time. So as you can see, it's going down. It has a changing velocity towards the end, and then this is when it like hits the ground. Then we'll go to the code. So the left and right, the left one is without drag force, the right is with drag force. The top part right here is the same for both. So as you can see, t equals 0, delta t equals 1 divided by 31, so it's 31 frames. And then the b is the magnitude of the drag force, which I found by just like messing around, like trying different values to make sure I can, like, it would be the same as the frames I got from the tracker. The while loop will keep going for the amount of seconds I have, and I just got those seconds from the tracker as well. So then this is the more important part. Between the two codes, this is the difference. As you can see right here, this line of code is commented on the left side, because this side doesn't count for drag force. So F net is just equal to W, and on the right side it's uncommented, and then we added it right here. So F net equals W plus D to make sure we count for drag force, and we just print both to get the frames. Alright, next we're looking at the graphs of observed versus expected. So the blue is the observed, that's the one I got from the tracker. The yellow is the expected with drag force, and red is without drag force expected. As you can see, like the blue and yellow are very similar. The blue just starts at 1.4 and then the yellow starts at 0, but the lines itself behave in a similar motion. The red is different because it doesn't account for the drag force, so it just reaches a faster velocity, and it moves more, it has like a higher position. Yeah. So what is the questions? The terminal velocity is reached when the drag force is equal and opposite to the weight of the object. So let's say like if the object was thrown, then it would reach the terminal velocity faster because it starts with a faster velocity. And then it would be different such that the object will be moving faster and will have the same path of motion. So as you can see back here, then the red, this has a faster velocity, so it would reach the terminal velocity faster in the beginning, but it still has the same path of motion like these blue and yellow ones do. So in this last sentence, the object will be moving faster, but it'll still have a similar path of motion to the original. So yeah, that's my lab.